You're muted, Professor.
There. All right, let's begin where we left off yesterday. We had a couple more examples to cover in this section, and then we'll finish up the last two, actually do the next two sections. All right, example number 9 said, sketch this function. X plus 1 squared. All right, so let's look at procedures, a method, a format, so to speak, on what we use to best understand how these to graph. First off, whenever you have a function to graph, identify your domain. In a rational function, it's a couple of things. One, find the x's that make the denominator equal 0. Those are your asymptotes, your vertical asymptotes. Then for the numerator, if we have special operations like radicals or once we have absolute values, find the limits of those. All right, so we have to understand what we're looking for here. And then as we've talked about so far, we have a couple things. Find the first derivative. What that's going to do is help us find our critical values. And then we'll know whether the function's increasing or decreasing. Then we find the second derivative. That's going to find us the point of inflection and concavity. So critical values, critical points, and everything like that. So once we have these, we have the basic shape of it. Because these are the important aspects of it. And then, of course, we're going to look for any symmetry and then other points. Whereas, if I look at the function, we know we can find the y-intercept and other values of our points. So what do we know about this equation? What's the domain of this equation? Well, looking at the denominator, can the denominator ever equal 0? No, because it's a positive function. It's a quadratic equation where it can never equal 0. What do we do about the numerator? Yes, it can equal 0. The y-intercept is at 1. Because 1 over 1 can give us 1. So we're going to get all these sort of things so far. Find the critical values. Because this is a rational expression, we know that we're going to have the denominator squared. So on top we have x plus 1 squared. The bottom we have 1 plus x squared. The derivative of the bottom is 2x. The derivative of the top is 2x plus 1 times 1 using chain rule. So doing the fishy thingy, we have 1 plus x squared times 2x plus 1. Oh, so it's irrational, so it's a minus. 2x times x plus 1 squared. So simplifying this, 1 plus x squared squared. Okay. So what do we have here? Can anything simplify? Well, we have 2x plus 1, we're going to factor that out. That leaves us 1 plus x squared minus x, and one more of those x plus 1s. It's 2x plus 1. We don't need the parentheses there. Let's fix on the inside. X squared minus x. X squared cancel. So we have 2x minus 1 times 1 minus x. That'll give us x minus x squared minus 1 plus x. So it's x, negative x squared, negative 1, positive x.
Professor, should that first parentheses say x plus 1?
I'm sorry? Did I
Going
mess
back,
that?
yeah, going back, when you first wrote the equation, it was 2 parentheses x plus 1, and then below that you put 2x minus 1. Right there.
Oh, yeah, they should all be x plus 1, shouldn't they? Right there. Good catch. That should be an x plus 1. Yes, that would change this whole thing because it would be a difference of 2 squares then. Then it would be 2x minus x squared plus 1 minus x. So the x's cancel. 1 minus x squared, rewrite down. 1 plus x squared squared. Good catch. Thank you so very much. That would have hurt if I kept on going. Okay, so that's my first derivative. So what can that tell us? If we set it equal to 0, the only part that can be 0 is the top. So it's 2, 1 minus x squared equals 0. Divide both sides by 2. So 1 equals x squared. X equals plus or minus 1. Those are my critical values. Ruh-roh. Now I have a much bigger one. I got to find the second derivative now. So that's going to be a much longer one. And the denominator is 1 plus x squared cubed, because we increase that one by 1. So on top we have 2 minus 1 x squared, 1 plus x squared squared. So negative 4x. 2, 1 plus x squared times 2x makes it 4x, 1 plus x squared. So we have negative 4x times 1 plus x squared squared minus 2, 1 minus x squared times 4x, 1 plus x squared. One plus x squared cubed. X squared squared. 4 times 2 is 8x. 1 minus x squared, 1 plus x squared. Can write that on the other side. Looks negative 4x, 1 plus x squared, squared minus 8x, 1 minus x squared, 1 plus x squared. And on the bottom, we have 1 plus x squared cubed. Okay, now we can simplify that. This is my second derivative. So on top, what do we have in common? We, for x, And a 1 plus x squared. We'll take out negative. That one's gonna, so I have one more 1 plus x2. Oh, I took out one of this, I took out this one. So it's 1 minus x squared in there. I took away one of those, and because that's out there. Negative 4x, 1 plus x squared. 1 plus x squared minus 2 minus 2x squared. Oh, I'm sorry, hold on, my bad. Hold on. This is supposed to be a 4. Because every time we double it. Now, simplify. Negative 4x, 1 plus x squared. 1 minus 2 is negative 1. X squared minus 2x squared is minus x squared. Right, so that one can cancel with one of these. And take out this negative here, so we have negative 4x. Take out the negative. So it becomes 1 plus x squared. Go to there. We can make sure everything's working out here. Okay. Those cancel, so we have 4x. No, if that was the case, okay, we had that. Let me backtrack again. So 2 negative 2x, so it's negative 4x. The bottom 1 plus x squared. So 2 times that times the inside, which is 2x, so it's 4x 1 plus x squared. Negative 4x times that minus 2 times 4x 1 minus x, 1 plus x squared. Okay, that looks correct. All right. Now I can factor out a negative 4x and a 1 plus x squared. Use 1 plus x squared plus 1 minus x squared. Okay. Negative 4, 1 plus x squared. This one becomes 1 plus x squared, plus 2. There you go. That's another mistake I made. So this becomes a positive 3. Minus x squared. Okay, that's right. Then we had negative 4x, 3 minus x squared, 1 plus x squared cubed, negative 4x, negative x squared plus 3, get rid of that negative. So factor out the negative, makes it a positive x squared minus 3 over 1 plus x squared. So I don't have any extenuous. So this is my second derivative. Be very, yeah, I can't stress enough, be very careful when you go through these things. It's always the signs that kill you. It's always the signs. The bottom cannot be 0, so we don't have any asymptotes. Set the second derivative equal to 0. That would be 4x x squared minus 3, which means 4x equals 0, x squared minus 3 equals 0. So x equals 0, and x equals plus or minus the square root of 3. These are my points of inflection. All right, let's see what we have here. Let's put these down. So my original function, let me write that one down. X plus 1 squared, 1 plus x squared, the first derivative. Two, 1 minus x squared, 1 plus x squared squared, and the second derivative. For x squared minus 3, 1 plus x squared cubed. So this one, my critical values are at x equals plus minus 1. My points of inflection are at x equals 0 plus or minus radical 3. All right, so let's look at the graph of this thing now. So the y-intercept, if you set x equal to 0, we get 1 over 1, which is 1. So at 1, we have a y-intercept. No vertical asymptotes. So how about horizontal asymptotes? Since the top will be x squared over x squared, the horizontal asymptote will be 1 over 1, which is 1. So there's your horizontal asymptote. Critical values at -1 and +1. So if we plug those into our original function, 1 plus 1 is 2 squared is 4. 1 plus 1 is 2. So it's at 1, 2, we have a vertex. Now at -1, we have -1 plus 1's at 0, so it's a 0. That's also our vertex. So we know that this, at 0, we have a point of inflection. So at 0, when x is 0, our point of inflection is at 0. And then at positive negative radical 3, just a little bit over 1.1 or 1.2. So that's a vertex, has to cross through there. That's a vertex. And that's a horizontal asymptote. So our rough draft of our graph, since this is a horizontal asymptote, it has to approach it as it goes to infinity. So our point of inflections are here and here. That's where it's concave down, concave up, concave down, concave up. So again, a lot of algebra in there. Remember horizontal asymptotes? Do we have to go back to how to find horizontal asymptotes? Y'all know how to find them? What
Yeah.
they are? You want to go over it or you know it? Because you have to know whenever you graph polynomials, the horizontal asymptote, the vertical asymptote, the x-intercepts, the y-intercepts, the point of inflection, the critical values. We have to know all of these. Because they will give us a rough draft of where the shape of the graph is. Let's look at another one. Example 10. Sketch this one. We have another radical, irrational, I mean. So looking at this equation, what can you tell me? Looking at this function, what can you tell me? With about any of these pieces of information. just by looking at it.
Well, the asymptotes, the horizontal and the vertical.
Okay, so where's the horizontal? Where's the vertical?
Horizontal, I believe, is at 0.
Nope,
No.
because the
Oh,
coefficient
I'm
of
sorry,
the
that's the
numerator is
vertical.
bigger than the bottom. It goes to infinity.
Yep. I'm sorry, I meant the vertical. The vertical at 0.
The vertical is at 0 because that sets the bottom equal to 0. Okay, what else do we know? Because the vertical asymptote is at 0 through the origin, we have no y-intercepts because you can't set x equal to 0. So let's look at the first and second derivatives here. X squared plus 4, 2x. So the derivative of that one's 2x, this one's 2. So 2x times 2x minus 2 times x squared plus 4 all over 2x squared. So we have 4x squared minus 2x squared minus 8. Four x squared minus 2x squared is 2x squared minus 8. So our critical values set the top equal to 0 is x equals plus or minus 2. That's where our critical values are going to be. Then let's look at our second derivative. We have 2x squared minus 8 over 2x squared, which makes it 4x, 2x times 2, which makes it 8x. Four x times 2x squared minus 8x times 2x squared minus 8 over 2x to the fourth. So we have 4x, 2x to the squared. Let's go ahead and fix these out. So we have 4x times 4x squared minus 16x cubed minus 64x over 2x to the fourth. Four 16x cubed minus 16x cubed minus 64x. So those cancel. So it's negative 64x. Actually, we don't have a horizontal asymptote. Why not?
Because the numerator is higher than the diameter.
Yes, because the top is bigger than the bottom, but there's a stipulation. The stipulation is if the top is bigger than the bottom by 1, you have an oblique asymptote. Remember that one? It's a slant asymptote. The way we figure it out is we do long division, x squared 0x plus 4. So what times 2x gives me x squared? 1/2 x. 1/2 x times 2 gives me x squared. Change the signs. So that disappears. So we have 4. So that's our oblique asymptote, is the graph 1/2 x. So the only thing we know about our graph so far is, since it's an oblique asymptote, starts from the origin, it's up 1 over 2. So that's all we know about our graph. It has that asymptote and the vertical asymptote here. So because of that, we know the graph's either going to be in this quadrant here, or this quadrant here, or here and here. It's either going to be in these two or these two. Since there aren't any x-intercepts, how do we know there are no x-intercepts? Because you can't set the top equal to 0. The only way a function can have x-intercepts is if the top is equal to 0. X squared plus 4 equals 0. X squared equals negative 4. We have imaginary numbers. So there are no x-intercepts. So therefore, our graph has to look something like it has to be in these domains. Our critical value is at 2, negative 2. So if I put into 2 squared is 4, 4 plus 4 is 8, 8 over 4 is 2. So it's at 2, 2. Same thing with a negative 2. It would be negative 2, negative 2. So that's my vertex. The vertex is at negative 2, negative 2, and at positive 2, positive 2. Those are my vertices. And because these are asymptotes, the graph has to approach them but never cross them. That's what the graph's going to look like. Let's do one more. An exponential one. Oh, I'm sorry. Let's just say, once we saw this function had an oblique asymptote, we didn't have to worry too much about the second derivative, really. because they really didn't show us anything. This is always going to be concave down. This is up. This is always going to be concave down. So, didn't provide us any other information. F of x equals e to the power 2 over x. So what's our domain in this function? Since this is an e function. Normally, the domain of e is what? What does e look like? That's what e looks like. E to the power a. It crosses at 1. But since our exponent is a rational expression, our domain now changes. What can x not be? X cannot be 0. So our domain has now changed to exclude the x value. Do we have any asymptotes? No, because it's an e function, there are no asymptotes. So the first derivative, eu du, so our u function is 2 over x, which is 2 over negative x to the power negative 1. So du is negative 2x to the power negative 2. So the derivative is eu du. So it's negative 2 over x squared, e to the power 2 over x. That's our first derivative. Do we have any vertices? Can we set that equal to 0? No, because the coefficient can never equal 0 because the denominator is x and e can never equal 0. So there is no vertex in our function. Vertices. Next, we look at the second derivative. So we have a product rule. So we have negative 2 x to the power negative 2. Actually, we have a quotient rule, to be honest with you. Should I leave it like that? Yes, let's go ahead and leave it like that. Let's do a quotient rule. So negative 2 e to the power 2 over x. The derivative would be negative 2 times negative 2 over x squared. The denominator is x squared, so it's 2x. So it's positive 4 over x squared. So it's 4. I forgot. I forgot the e to the power 2x. So the x squares cancel. So we have 4 over e, or x squared, e to the power 2 over x times x squared minus 2x times negative 2e to the power 2 over x all over x squared squared, just to the fourth. So the x squares cancel. It's 4e to the power 2 over x plus 2 times 2 is 4x e to the power 2 over x all over x to the fourth. We can factor out a 4e to the 2 over x, which leaves 1 plus x over x to the fourth. So that's my second derivative. If we set the second derivative equal to 0, the only part that can equal 0 is the 1 plus x. So we have a point of inflection at -1. We have no vertices, and we have a one point of inflection. So we have no vertices. Okay. So x cannot be 0. So what's it on the positive side? When x is positive, when x is bigger, so this gets to be a fraction. Whenever e has a fraction, that means it's a decreasing graph. So the graph from where? Anyway, it just keeps on going. Okay, so in our values here, we have a horizontal asymptote. Since x cannot equal 0, e to the power, so in other words, it cannot cross 1. It cannot cross 1 because our original function is e to the power 2 over x, and x can never equal 0. So when x is equal to 0, it's at 1, so there's a horizontal asymptote. E can never be negative, so this is the first part here. This is the positive aspect. So when x is greater than 0, that's what the graph looks like. Now, when x is less than 0, because x cannot equal 0. This function can never be 0, so nothing down here. So at 0, this is a decreasing function. And we have a point of inflection at -1. So at -1, we have a point of inflection. So it's e to the power -2. E to the power -2. And that's an asymptote. So it's going to be concave down here and it'd be concave up here. It can't go to 0. So that's going to be a rough draft of the graph. Again, there's a lot of algebra involved here. And this part just deals with a lot of observing the graphs parts of it. Because the function itself, we have to know what the E function looks like. And since for X being negative, it's a decreasing, or it's now it's on the bottom, so it's now an increasing function. So that's why it's increasing that way. And for X being over here, since it's a fraction, it's a decreasing function. All these things, again, you have to remember from algebra. That's the end of that section. Woo, I apologize. But